Hey class, we're back again and we're going to look at chapter 8.5, which is similar objects, scale models, and scale diagrams. So the learning target for this lesson is to understand and use scale models for 3D objects to solve problems. So in order to do this, we need to understand what similar objects are, and that's going to be two or more 3D objects that have proportional dimensions. Now before we jump into 3D, what I wanted to show you is how you can prove this with a 2D figure, and then it's not so hard to kind of extrapolate it to a 3D figure. So here we have two triangles, and I've actually just drawn this triangle and copied it and pasted it. So these triangles are exactly the same right now. So what I'm going to do is I'm going to show you the idea of similarity. If I can just grab this triangle, and what I'm going to do is I'm going to try and drag it up, and you'll notice that I'm trying to preserve the angles. I might not be doing the best job of it, but let's just say I make it 3 times as big. So these two things would be similar. Now I know you're saying this is 2 dimensions, but I think you're going to see where I'm going with this. So let's put some measurements on this, and let's just pretend that this was 2, 3, and 4. And let's pretend the angles, and again, this is not real, but just making this up. Let's call this 40 degrees, call this 60 degrees. So the 40, 60 is 100, so this is obviously not 80, but let's pretend like it is. Okay. One thing I mentioned in a previous video is that the angle relationships are preserved, so this would still be 40 degrees, this would still be 60 degrees, and this would be 80 degrees. Again, it looks nothing like it, but that's okay. Now imagine that I tried to get this 3 times as big, so what would end up happening is I would get 3 times 2 is 6, I would get 3 times 3 is 9, and I would get 3 times 4 is 12. So someone might give you these two figures and say, hey, can you prove to me that these are actually similar? And the way you would do that is you would check the proportions of the sides. So what should happen is if I take how this side length is mapped onto this side length, if I find the ratio between those two, like if I find 6 to 2, well, 6 to 2 is a ratio of 3 to 1 or just 3. So what should happen if these are actually similar is that I should be able to take the ratios of the other two sides. And if we try that, let's go 3, and actually I want the larger side on top like I did last time. So 9 to 3, and that would produce a ratio of 3. And then lastly, if I did 4 and 12, well, I would be looking at 12 is to 4, and I would get a ratio of 3. Now what's really important is that I could have done this the other way around. I could have done 2 to 6 and got 1/3, 3 to 9 and got 1/3, and 4 to 12 and got 1/3. But the really important thing, and how we know that these are actually similar figures, is that the ratio, the proportion between the sides, all came out to actually be the same. So if we look at a quick 3-dimensional example, the only thing that's going to change is that instead of just having lengths and widths, you're actually going to have depths as well. So you'll notice here that we have 2 pans. We've got a larger pan with a 30 centimeter diameter. Its depth is 6 centimeters, and its handle length is 24. And so the smaller pan is a diameter of 20, a depth of 4, and a handle length of 16. So when asking if these are actually similar figures, what we would do is we want to set up a comparison. So let's set up 30 centimeters compared to, or what's the proportion or ratio between the diameter of the other pan, which is 20. Okay. And then we could try and set up, we want to see if that's going to be equal to, say, the depth of 6 centimeters compared to the depth of 4 centimeters. And we want to see if that is the same as comparing a depth of 20 centimeters, or sorry, handle length of 20 centimeters. Sorry, I'm messing this up. A handle length of 24 centimeters to a handle length of 16 centimeters. So I want to check, are these proportions actually the same? So it's not too hard to see that both of these are divisible by 10. So by factoring out a 10 from the numerator and denominator, we could create a 1. And this ratio simplifies to 3 over 2. Looking at this ratio, we've got 6 over 4. Well, 2 will go into 6 3 times. 2 will go into 4 twice. So at least those two dimensions are in proportion. And then we look at 24 and 16. Okay, well 8 will go into 24 3 times. 8 will go into 16 2 times. And you'll notice because all of the dimensions are in proportion that these are in fact similar figures. And so that's it. That's all there is to it. Basically, you're just trying to find the ratios and see if that ratio is consistent throughout all the dimensions.